Hello everyone, welcome back to Nuclear Materials. Today we'll be covering cladding, including austenitic stainless steels, phoritic stainless steels and zirconium, and then we'll discuss the observed irradiation effects and how we can mitigate them. So first and foremost, what do we actually want from a cladding? Well, as listed in your notes on page 51, the fundamental requirements are to isolate the fuel from the coolant, which requires chemical stability and mechanical integrity, to have a low neutron absorption cross-section, which allows neutrons to pass through the cladding without being absorbed. They need to be corrosion resistant, and in general that means also being compatible with the fuel and the coolant, because that's the two different substances they're going to have to come in contact with. They got to conduct heat well, because you've got to get the heat out of the fuel through the cladding and to the coolant. So heat transfer from fuel to cladding needs to be considered, as well as the heat transfer through the cladding. High melting point is quite important, and it's got to be well above the operating temperature of the reactor for reasons I really hope you can predict. You've got to have fair amount of strength and ductility, especially to withstand any swelling of the fuel, which by now we're well clued up on given the previous lectures. Much like fuel, you've got to have pretty high stability under irradiation, and you've got to have a low induced radioactivity, because that's going to help you when you go to recycle your fuel and your cladding after you've used it. Now, improving the performance of cladding is critical, as is often the cladding that limits attainable burnup. And as we'll see, there are a number of options for us to choose from, first of which we're going to look at is austenitic stainless steels. So, austenitic stainless steels are CCP structure, so cubic close packed. In low carbon steels, austenite is only stable above the eutectoid temperature, which is around 723 degrees Celsius. But different alloying additions can stabilize that austenite phase at lower temperatures. Austenitic stainless steels are the cladding materials of choice for fast breeder reactors. Remember, the ones that use fast neutrons and breathe their own fuel, where the operating conditions are quite, particularly severe, where you're going to get total damage accumulating to up to about 100 displacements per atom. And you've got liquid metal coolants in those reactors, and they range from 250 to 700 degrees Celsius. So a real challenging environment to have a stable, reliable cladding to work from. Fortunately for the metallurgists, however, you will know already the most commonly used alloys, 306 and 316, the composition of which I've shown you in this table. The main challenges for these alloys as cladding are phase instabilities, void swelling, creep, and mechanical property changes. And unfortunately, all of those are interlinked. However, it's swelling really that is the main concern with stainless steel cladding. Why? Well, irradiation of austenitic stainless steels induces transmutation, notably to form helium. Nickel is the key element relating to helium production, and so the greater the nickel content, the greater the amount of helium produced in your alloy. So you get a neutron, it comes through. The most important reactions are nickel 58. It absorbs a neutron, becomes iron 55, because it absorbs that neutron and it spits out an alpha, as shown in your notes here. And then you've got the nickel 58 going to nickel 59, which then decays by alpha decay to iron 56. And the worry there, in both of those reactions, is that alpha particle that you're spitting out. The generation of that alpha is what we're worried about here, because the particle will gather electrons and become elemental helium. And the figure below shows the cross-section for these neutron absorptions and for the alpha emission reactions for those main species in a stainless steel. So you can see that nickel is the biggest worry, as it has a much larger cross-section. And obviously in a stainless steel, there's a lot of nickel. So why are we worried about helium? Why is it such a problem here? Well, due to its small size, a helium atom can very easily diffuse interstitially and form bubbles. However, as I've mentioned before, previously in the course, voids observed in materials are much larger than can be explained by the production of helium alone. And that's because of something I mentioned before, 3 words, gas-assisted nucleation, meaning helium bubbles that form from all this helium you're making from transmutation will act as sinks. They're tiny, but they act as sinks for vacancies that travel randomly and sit in these sites, and therefore they become nucleation sites for voids, and that in turn accelerates swelling. So you've got gas-assisted nucleation of voids. So the incubation period after which you would normally expect swelling to occur is shortened significantly when you've got helium being produced. Now, austenitic stainless steels have good dimensional stability under irradiation until the onset of void swelling. So the figure at the top there shows void swelling behavior as a function of radiation dose, indicating the different stages. So you have initially the incubation period I just mentioned, which is the neutron dose required to produce sufficient helium to make void nucleation possible. And that's going to depend on a number of factors like temperature, alloy composition, and the microstructure, because obviously you've got different nucleation sites. It's going to affect how quickly these bubbles grow, or voids grow. After that incubation period, next up you've got the transient stage, and there you have where swelling enters steady state. Typically around 1% swelling per displacement per atom, which, to give you a perspective, is much higher than for Phoritic steels, which earn themselves less than 0.1% per dPa. So you're getting 10 times the swelling rate, steady swelling rate, in austenitic rather than a Phoritic. And within steady state swelling, you're going to have 3 regimes. And that's shown in the figure at the bottom of page 53. You got, for 316 stainless steel at least, that graph shows, you got low swelling at high and low temperature, but high swelling at moderate temperatures. Why? Well, the low temperature state involves direct recombination of vacancies and interstitials because they've got lower mobilities at lower temperatures. So the low temperature state involves direct recombination of those vacancies and interstitials. So the swelling rate is therefore low, but increases gradually with increasing temperature as you increase the mobility of your vacancies and your interstitials. And at moderate temperatures, the steady state swelling rate is high and can only be explained by an excess of vacancies. And at high temperatures, the swelling rate decreases again with increasing temperature, since the rate of vacancy emission from the voids is greater than the flux of vacancies joining the voids. So it's, they're battling each other, but when you get to high temperatures, more are being emitted than the flux coming in to grow them. So the swelling goes down. And that swelling can be incredibly large, up to 88% by neutron irradiation, although you can get hundreds of percent should you choose to massacre your material in a proton beam experiment. And that degree of swelling as a function of temperature is shown in these micrographs on page 54 at the bottom of the page there, with very large voids forming at 650 degrees Celsius compared to the smaller ones at lower temperatures, which makes sense with what I've just described about our different regions and our temperature dependence. And should you wish to see the effects of swelling on a macro scale, here is an image of an unirradiated stainless steel rod versus an irradiated one, indicating the sort of increase in volume. This rod in particular was irradiated to 33% swelling by neutron irradiation. That's equivalent to about 75 displacements per atom at 510 degrees Celsius. And as you can see, all relative proportions have been preserved. Now, although that is the case, if you were to look across a fuel rod assembly, so a whole fuel assembly, you might see something like the image below. What you're seeing there is the top of the two different fuel assemblies after irradiation. Figure A shows an irradiated bundle of fuel rods with various heights due to the variation in dose that you're getting across those fuel pins. And, most importantly, non-uniformity in composition and texture of the rods. So because the composition and the texture were different, the rods are going to react differently to the swelling. Whereas if you look at image B, on the other hand, that shows an irradiated yet undistorted assembly because they've used swelling resistant cladding irradiated to effectively the same dose. And that indicates the significance of ensuring you've got uniformity in the production of your rods. You do not want the fuel assembly shown in figure A. You want it shown in figure B because you imagine it can be a nightmare to control a reactor where the fuel is not where you think it is. You're going to get hot spots and it becomes a bit of a nightmare for almost everyone involved. Reactor physicists will not be happy if you give them a dodgy cladding where all the fuel rods change in shape to one another. Okay, so what does sort of swelling resistant cladding look like? I mentioned it for B. Well, for 316 stainless steel, if you look at the graph in the center of this page here, page 56, you see the effects of cold working and also the additions of phosphorus among other elements. The reason why they add phosphorus to try and get this swelling resistant cladding is because it forms precipitates. And similar to the way that voids like to form, well, the surfaces of these precipitates act as sinks for vacancies. And that reduces the vacancy supersaturation, which limits swelling. So you've got a more swelling resistant cladding. Cold work can also have benefits because that creates dislocations, which again will act as sinks for vacancies, all of which inhibits swelling by prolonging that incubation period prior to the initiation of swelling. That's what you're trying to do. You need to prolong that incubation period to stop that swelling occurring. Okay? So that's what a swelling resistant alloy looks like. Unfortunately, there's other phenomena that we need to be worried about. As always in nuclear, there's multiple problems. And one of those important phenomena we need to be aware of is the inverse Kendall effect, as this effect can cause compositional variation across our cladding, for example. Now this effect is represented in the graphs to the right here on page 57 as the motion of a boundary layer between two different metals, A and B. And it's due to the different diffusion rates of the two metal atoms. So let's take A. If the diffusivity of atom A is faster than that of atom B, then there is a net flux of atoms from A to B. So the boundary appears to move to the left, which is shown in the second image. Yeah? However, you can also view this, it might be easier, as being a net diffusion of vacancies in the opposite direction, rather than the atoms themselves. So the atoms A are mostly moving to B, but in order for that to happen, vacancies from B are moving to A. So in that case, the number of vacancies in metal A is low and is high in B. So the net flux of vacancies is from B to A. Okay? Yeah? The net flux of vacancies is from B to A, but the net flux of atoms is from A to B. So why are we interested in this? What does it do? Well, when a flux of vacancies drives an opposite flux of mobile atoms, in this case A atoms, we call this the inverse Kendall effect. The results of which are faster diffusing species become depleted at vacancy sinks, whereas the concentration of the slower diffusing species increases at the sink. So in stainless steels containing voids, you can get significant variation in composition surrounding a void. And what happens when you have significant changes in composition? You can get phase transformations. And phase transformations lead to different mechanical properties, corrosion properties, etc., which we do not want. In stainless steels, one of our main species, we've got chromium, iron, and nickel. Yeah, chromium diffuses faster than iron, and iron is faster than nickel. So if we're thinking about the inverse Kendall effect, that means chromium and iron diffuse away faster from voids and cause ferrite to form away from those voids as it becomes depleted in nickel. And that means that only regions close to voids remain austenitic, because nickel is an austenite stabilizer, and nickel is slow and stays by the voids. So you start to get the voids staying, the material around the voids staying as austenite, but the regions around it transforming to ferrite. And obviously ferrite has very different corrosion properties. So I've mentioned before how dislocations can be produced during irradiation, but it's a little bit more complex than that. Depending on irradiation conditions, an alloy will show an equilibrium dislocation density that is eventually reached under irradiation. You get this equilibrium dislocation density regardless of what condition you initially put the alloy into be irradiated, be it higher or lower than the original dislocation density, basically. And that's what you see in the figure on page 58. If you look at that figure, you can see that at a relatively high dose, both cold worked and solution annealed stainless steel will reach the same dislocation density after irradiation. Cold worked reduces the dislocation density in number. Solution annealed sees an increase in the number of dislocations. And that occurs because there is a balance between irradiation causing an increase in dislocation density, but also causing an increase in mobility, which allows dislocations to be removed. So those two processes are battling each other. And in cold work samples, the increased mobility means the dislocations are removed a lot faster than they are created. And the opposite goes for the annealed samples. They're created faster than they're removed. And eventually, these two battling processes equal each other out, reaching the same steady state value, which itself will depend on the radiation temperature, neutron energy, and several other factors, but that's beyond the scope of the course. The point is, regardless of how you put your material in the first place, if you have a significant enough dose, it will reach the same steady state dislocation density. Okay. So although we've talked about radiation hardening, actually what you can get is radiation softening. Now we'll look at creep. So stainless steels for creep, we know that from our foray into fuels that irradiation can accelerate creep or initiate it at temperatures below that where we wouldn't expect thermal creep to occur. Well, the same goes for stainless steel cladding. You can get creep accelerated by orders of magnitude, which is what you see in these graphs here on page 59, which you're welcome to peruse at your will. Not only that, but creep is accelerated by swelling, as shown in the graph to the bottom right there, with swelling rate on the x-axis and a creep coefficient on the y. So it's very similar, the effects of creep. The key point is accelerated by swelling. But you can read up on that further. That's about how much we really need to know for the time being. What about mechanical properties? Well, again, We get irradiation hardening and a loss in ductility on account of the increase in dislocation density, and that's shown in the top right graph. However, like I've said, the effects are temperature dependent, as shown in the bottom right graph. That shows that at high temperatures, irradiation can lead to softening as the lower steady state dislocation density is reached. So you've got yield strength on the y-axis, neutron fluence on the x. High temperature, you get something very different to low temperature. You get hardening or softening. Okay. Now, when it comes to the fracturing of such irradiated stainless steels, you may see something like this. The image at the top here of page 61 shows a heavily irradiated 304 stainless steel sample with a shear band across the centre, within which voids have been sheared. Now, of course, swelling leads to catastrophic weakening, eventually causing fracture. And that's shown in the following two graphs. The lower image showing the fracture surface of a brittle stainless steel 316, which was irradiated at 640 degrees Celsius and then bent at room temperature. And it just shows that you get this loss of ductility. So you do get catastrophic failure, and you get the shearing of those voids, which you can see along that deformation band. And really, that's stainless steels. We've covered a fair amount there. We've covered a number of areas, but the key effects of irradiation are helium formation and void swelling can occur. Steady state swelling rate depends on temperature. Swelling is accelerated by stress. The inverse Kendall effect leads to transformation of the matrix to ferrite, only leaving austenite regions close to the voids, so we start to get different corrosion risks. Dislocation density may either increase or decrease on irradiation depending on the original dislocation density, and it always tends to a steady state value. Creep is accelerated by irradiation and swelling. Irradiation induces hardening and loss of ductility, and the gap between the yield strength and the tensile strength narrows because of that loss of ductility, obviously. Irradiation at high temperature can lead to softening, sort of reiterating the point there, and swelling can eventually lead to catastrophic failure with weakening and embrittlement. And should you be able to recite that list and understand or describe the mechanisms behind each point, you should be well prepared for a question on stainless steel come your exam. And that's it for part one. In part two, we'll move on to phoritic alloys and zirconium cladding and look at radiation effects in those. So I'll see you soon.